Hey guys, welcome to Ubiton AI Labs. This is episode 3. I'm Sándor, and in this episode we are going to build a variational autoencoder. And we are going to make Granny smile. So we are going to build this and much more actually. But before we go anywhere, let's go back to our first autoencoder notebook from episode 1, where we approximated the cat, reconstructed the cat among many other images. We used the kind of built-in Cypher10 database. And let's scroll down here, open up a new code block, and let's sample this latent space randomly, see what it gives. Because as you recall, we encoded images into this latent space, which became latent vectors. So they are points in this latent space. And we even interpolated between these vectors and got kind of a meaningful, smooth transition between these images. But what happens if we just take random numbers in this space and sample them? So we torch nograd. Let's generate a random number, R. Rand n, and this is the batch size, and our latent dim variable contains it's 384. Now we have our model declared on the top, and let's reconstruct an image using the model decoder and this random number. Now we can display the image just as we did before, like this. But I need to rerun my notebook. So I just retrained this notebook, so you don't have to. You don't need to follow me. It will be just a small demonstration. So just to check, and I'm moving this tensor to the device, but not here at the end. This, we created a random number according to the latent vector shape and decoded it. This is, all numbers are between 0 and 1. As you can see, it has not much to do with our data set. Let's try randomly sampling from the latent space. It's colorful, it looks, well, you decide how it looks, but it's definitely not anything close to our data set. And pull up the notebook from the second episode, the previous episode. This is where we left off. I logged the performance of the network. We don't need that anymore. I'm just cleaning it up a little bit, and we will start from the beginning. So we already have these installed, so we can remove. And the data set for this exercise will be the same, the faces 128. You can use any other data set as long as it's in this format or you format it yourself. It doesn't matter. And we didn't have this group norm here last time. I just added it myself, so we don't need that. Before we get to implementing the variational autoencoder, we must discuss what it is, because there is some theory behind it that we need to get familiar with. So I'm pulling up a Google search now with the normal distribution, and you can see that on this image. You're probably familiar with it. So basically, when you sample from this distribution, the most likely number that you will get, the most number you will get from this is 0. And then as you go outside, basically 99% of the numbers that you sample from this distribution will be between -3 and 3. Given the mean is at 0 and the standard deviation is 1. So this distribution has two parameters. Its mean, basically its center of the bell curve, and its fatness, the standard deviation, how wide it is. And there are multiple examples you can find on the internet. So this is in one dimension. You sample from this distribution and you get a scalar, one number, a real valued number. Let's up this and go up to 2 dimensions. A bit smudgy, but it will do. So we have 2 probability distributions here, both normal distributions with slightly different parameters. And they are projected on this 2D plane, the samples drawn from these. So one coordinate of this point is drawn from this red distribution. The other coordinate is drawn from this blue distribution. You can see X here and Y here. So if these were both with mean is 0 and standard deviation 1, then this scattered area would look like basically a circle. But some parameters, the mean and the standard deviation, are modified on either of these distributions. So the area is a little bit, it looks like as an ellipse. This is in 2 dimensions. But we have, in our example, more than 300 dimensions, or maybe even 500 or 1,000 dimensions. So going back to the original autoencoder, again what it did, it converted the image into a vector in the latent space. Many images into many latent vectors in this latent space. And it kind of learned how to cluster it as the network optimized itself, because that's just the reduction of entropy as it happens. But those are basically separate vectors. What the variational autoencoder changes is that it doesn't project the image as a single latent vector. It creates an n-dimensional probability distribution in this latent space. So imagine it like as a cloud in a very high dimension. And then what you pass to the decoder is a sample taken from this probability distribution. This means the encoder is estimating the mu and the sigma, basically the mean and the standard deviation of the probability distribution for each dimension in this latent space. So you will end up with a mean and basically a log variance, not a standard deviation. And you can sample using these 2 parameters from this high dimensional space. You pass that to the decoder, and because one image encodes into these two parameters with one, and we call this like, so you have two parameters for one image. You can use that to sample multiple times. So basically, the same input image can result in multiple output images. And we use the mean square error loss so far for the autoencoders. Here. And we are going to keep this. It's nice. But if you just use this, there wouldn't be any guarantee. Basically, the network could change the mean and the log variance for each dimension of the latent space as if it as it would like in any arbitrary way. And we want to sample from a normal prior. And we would like that the end result of this optimization and the latent distribution, it should resemble this normal distribution as much as possible. Therefore, any deviation from a normal distribution, we will penalize using the Kalbeck-Leibler divergence. This measures basically the kind of the distance between two probability distributions. So if our latent distribution gets further and further away from the standard normal distribution with mean 0 and standard deviation 1, that will increase our loss. In this way, the network, as it tries to reduce the loss, it will every time will pull back the distribution, and in this latent space, every latent vector will be arranged kind of between -3 and 3 in a very high dimension. So like almost, there will be points outside of it, of course, it's a probability distribution, but most of the numbers will be in this area. Now this ensures that going back here and running it a bit more, having a continuous probability distribution in the space and working with distributions instead of individual vectors, it ensures that if we traverse this space, mostly between -3 and 3 in all dimensions, we can sample any arbitrary random points in it, and we will still have meaningful images when we decode them. So the encoder, it takes as input our image, it outputs the mean and the log variance in this latent space, and the log variance is just the standard deviation squared, and why we calculate the log of it, it's because the variance would be really, really small. And if we take the log of it, we can scale it up, and due to floating point arithmetics, it's just easier to calculate. Now, then we sample from this dimension, from this space, and feed it to the decoder. And the output of the decoder is actually the numbers, each pixel intensity for RGB each, are treated as probabilities from the Bernoulli distribution. So the decoder itself is learning a likelihood distribution Px given z, then z is our latent vector. Without going really deep into mathematics, because I am personally interested in actually implementing the stuff and understanding it to the level that is needed to do awesome things. I'm not going to write page-length formulas, but let's start instead to implement it, and we will discuss more during implementation. So we load our data set. That's cool. We don't actually need to display this image here. So let's load the data set. And we had these encoder blocks here as they are. And let's just disable the dropout for now. So with dropout 0, this will not take any effect. We can even leave it there. It doesn't hurt. So the encoder here, as I said, it will not output the vector itself, but it will output the mean and the log variance of the normal distribution that we are after. So let's create two layers, fully connected for mu, the median, a linear layer. Let's take this, move it to a variable like encdim, and we can remove this single layer from here. So up till just flatten. And we map from encdim, which is this, the number of neurons in this is actually encdim, to the latent space. And we have the same for the log variance. This is our input image. We run this encoder block. Then we take H, feed it to FC mu and FC log var. That's all the change we need for the encoder. Now the decoder, dropout is set to 0, that's great. The decoder actually, we could move out this also to a variable, just in case later we need to change it. And that's all the use for it right now. Okay, decoder stays the same. Run the code. Now this we cannot run anymore because this returns two values, so we cannot directly feed it to the decoder. We could just delete this block. Now for the cool part, the autoencoder module becomes our VAE module. We have our encoder and our decoder, and when we sample we get mu, log var, and as I said, we cannot pass it directly to the decoder because we don't have a Z. We don't have an actual vector, a sample from the distribution in that space. So what do we do with this? We define a function. It's called reparameterize. It takes mu and log var, and we calculate a standard deviation using torch.x 0.5 times log var. And we create an epsilon, which will be a random variable taken from the normal distribution, rand n, like std, because logvar is of shape 1 latent dim. And we return mu plus std by EPS. So this basically samples from our distribution that we create. And why do we sample like this, and why do we call this reparameterize? Because we could sample using torch normal, and we could provide mu, and we calculated std and just return that. But during training, since this has no derivative, we couldn't train on this. There would be no gradients, and backpropagation would just break here. That's why this is called the reparameterization trick, so that this value can be derived and gradients can keep flowing through it back to the encoder. So here, actually we can make this a static method. And here we use self dot with mu and logvar. So now we have mu logvar z, our latent vector, and our decoder uses z to decode our reconstructed, it reconstructs the image basically. And we return y, the latent vector, mu and logvar. It's a lot to return, but everything will be used. Now let's go to the training code. And before we adjust anything, let's take this part where we declare the model, cut it, create a new code block and paste it here. Rename autoencoder to VAE. Having the model in a separate block is great because we can run training multiple times on the same model because the state will be kept. So we can further train our model if it doesn't fit. On the other hand, don't forget, if you want to retrain your model completely, then you need to wipe the model, recreate it using this block. So you need to rerun this block. Currently we have 13 million parameters. For now, I would like to disable this cosine annealing LR. Later we might use it, but we have the initial learning rate set to 2e-4. And if we just use that here as the final learning rate, then practically this will have no effect. Okay, so our model forward pass returns 4 variables. We will deal with calculating the loss in a bit. So we need to modify this part. Let's call this y hat. And we pass y hat, y, mu, and logvar all to the calclogs function. We should call this VAE loss. Same thing happens here. We can, either you can comment this line that adds the image noise, or I will just remove it. Change this one, but don't pass Z, don't pass Y here, the actual output that we want. And now it's time to actually implement the VAE loss. So we have y hat, which is our reconstructed image. Y, the actual image. We have the means and the log variances of our distribution. So the loss here, as I said, will be made up of two terms. One is our MSL loss. Let's just call it loss 1. It's the mean square error loss between y hat and y. But in order to keep these distributions close to our prior distribution, the normal distribution with mean 0 and standard deviation 1, we have to penalize if the mu and the log variance makes the distribution distorted. So we are using the KL divergence loss. That will be KL. And I'm just going to write the equation. That is it looks like this. If you want to go deeper into the mathematics, you can find plenty of resources. I'm just going to write it as is and know that it penalizes if the distribution tends to move or distort further away than our target distribution. So we return loss 1 plus KL, and also just for analytics return them separately as well. This is the total loss. This way, now this loss function returns 3 parts. And let's call this loss MSE and loss KL. Don't forget to rename this function as well. Do the same thing here. All right. We are tracking the loss using min loss we don't actually use. Not until we save our model to a checkpoint. To use the losses array, we detach the loss. This is not used. Average train loss, yep. Learning rate will still be printed. We can print these as well. If you want. Running into an error. Probably because our shapes, because we weren't able to run that code that checks if the encoder and the decoder is the same. So y hat z mu log var model x. So I made two issues here. One is that I accidentally made typos and passed x to fc mu and fc log var, which you probably noticed even before me. So let's fix that. The encoder should be fine. And in this case, because it's a static method, you don't need self. So my training finished and I'm back. Before we continue with more, I like to paste here 3 utility functions. You don't need to type all these now. You can join the Skool community and download the entire notebook, including these functions. It's entirely free. So there is GIF show and GIF save. Both take a list of images in the shape of a Dodge tensor. And this displays an animated GIF inside the notebook. This saves it to a file. And EM show we already know from the previous episodes. Okay, so we have a trained model that represents a continuous normal distribution, like distribution in this large dimensional latent space. Now, since we already know that sampling random numbers from our normal autoencoder yields garbage images, let's try sampling random numbers from here. So just as we did, actually let's keep this code and open a new code block. You create a random latent vector using torch.randNormal, the shape of one latent dim. We move it to our device and we reconstruct an image using only the model's decoder, RZ, and display this image using EM show. Remember, this also has the batch size as the first dimension. So this will be imgrec squeeze 0. Actually, I didn't run this, that's why it's printing an error. So we have this face. It's a totally random vector. And if we repeat, so what actually happens when you use the default reduction, which is mean, is that the loss is calculated per batch, right? And the MSL loss calculates, if you provide reduction none, it calculates per sample the loss. So this loss then will be a vector as long as your batch is. But if you provide or not provide any reduction parameter, and then it will use the default, which is mean, it will take all the losses in your sample and average it. And in case of the variational autoencoder, this results well in the image that you saw. Now with sum, it means that this loss will be a number, but all the mean squared error losses for each image will be summed up. Thereby, the loss, of course, the total value of the loss is higher because it's not the average, it's the sum. And now if we sample our guy, it's still smudgy, but we have a much better reconstruction. Okay. So this is an image fully reconstructed. But we already saw here how a normal autoencoder, when you sample randomly from the latent space, it basically throws out colorful garbage. Let's try the same here. Add the new code block. model.eval, just to be sure, with torch.nograd. Let's generate a random z, call it rz, torch.rand n, or it could be even rand. It draws from the uniform distribution. Now the shape of it must be like we have one batch. The batch size is 1 and it's latent dim long, and move it to the device. So this will be a vector containing random numbers drawn from the uniform distribution with a size of 1 and latent dim. It's actually a matrix, but whatever. And we could even multiply this, but let's keep it for now. And let's reconstruct an image from this completely random vector. emgric equals, we call the model decoder with this rz. And if I remember correctly, the model decoder only outputs the reconstructed image and nothing else. So as you can see, we have our em show here. Delete it, because I'm going to provide you utility functions for playing around. Open a new code block here, and you don't need to pause the video and type this all. You can find this Python notebook in my Skool community. Link is in the description. It's free. The notebooks are free. You don't need to pay anything. You can copy it from there. It's nothing machine learning specific. There's a GIF show function. It takes frames in forms of a torch tensor, so a list of images, and you can display an animated GIF inside the notebook. Similarly, GIF save, it works the same way, but it saves to a file, and we have our em show function just as before. So now run this snippet, and we can em show our image reconstructed, but squeeze it on the 0th dimension to remove the batch size. And you can see we have a face. We can click this. Remember, these are completely random vectors, and we can even multiply it. Test a little bit. Let's multiply it by 2. See what it gives. As you can see, sometimes it starts to give garbage, because if we multiply it by 2, then it might be outside of the bell curve, and we have no distribution there. But it's still much more meaningful than what we have here. Now, this was trained on Cypher 10, so it's not an exact proper comparison. But as you can see, these are still faces. Okay. So interpolating between two images. Let's try if that works here. This is from the last notebook. We have to extend this here, which is, this is mu and logvar for both. Let's make this half. And yep, looks like it works. Let me clear this cell output. We don't need em show anymore. And let's take this code piece insert a snippet here, and pick an image from, let's say, from our train data set, which is 5,000 long. Let's pick 17. We don't need this random vector anymore. And I think I can just pass it, right? You can copy this. Let's make the variable names consistent. So we have a reconstructed girl. Okay, that's cool. We did that already with another image. But let's work now with mu and logvar. So let's take VAE, reparameterize, and generate a new latent. Let's say that imgrec is model.decoder from this Z. And click this many times. As you can see, because we are sampling from a probability distribution, the same mean and log variance, obviously because reparameterize uses a random number, with these two parameters we can generate similar, very similar, but different images. Now, for fun, let's do this 100 times. Let's say Z is a batch of 100 now. This is an array, so we need to torch.cat. And by default, so you can see here, it concatenates on dimension 0, so you don't need to write it out. I'm going to be explicit with it. And now we can show it with image show, and I don't even want to do that, because we have our nice GIF show, and you can just pass image rec to it. We can increase the duration 5,000 by 10. Next example. Let's go back to our interpolation snippet here. And copy it. Actually, sorry, we already have this. It's using linspace, so we can build from this. You can even pull from the test data set. It shouldn't matter because our model converged to a pretty good solution. So what we did here is we have an alpha, which is a vector that goes from 0 to 1 in 25 steps, and the beta that goes from 1 back to 0 in 25 steps. We transpose them. So the shape becomes from 25 to I guess 25, 1. Concat them, it becomes 51. We can just remove this code, we already have the utility function. And we have this Z. We can say frames. So this will decode a batch of images that are interpolated from ZA to ZB and then back from ZB to ZA. And don't forget to add, I'm just going to add dashes here because we are not using it now. We can increase the speed by lowering the frame duration. Okay. Now we can see this is a kind of smooth transition, but to put it in contrast, let's compare it with a standard normal linear interpolation where you have just two images and a number between 0 and 1 and you mix them together. So we have our frames here. And let's say we declare LA. We have image A. Move it to the device. Unsqueeze. This way we add a 1 prefix, which will become the batch size. So the size will be 1, 3, which is the RGB channels, the height and the width. Then there is a cool function called repeat in PyTorch. And basically with this, we are going to repeat this one image 50 times along axis 1. And it's because, so here you must provide as many parameters, as many dimensions your tensor has, in this case 4. Trying to annotate it, so here we have a 1 batch size because unsqueeze adds a batch size. We have channel, height and width until here. And then with repeat, it becomes 50 channel, height, width. Let's do the same with image B. And what we would do here to get LC is similarly as we did the interpolation here, but we were interpolating with latent vectors. Now we just interpolate the images themselves. So 1 minus phi times LA plus 5 phi times LB and try to run it. Error. It's expected because these shapes cannot be multiplied. So size of a tensor 50 must match the size of a tensor 128 at non-single. So phi has a shape, and what's LA's shape? And it cannot broadcast it to these 3 dimensions. A quick trick is to flatten these into a single number and then shape them back to this. So we flatten down, we multiply by phi, and we reshape them to this. And we can do that as like view phi.size, which in this case will be 50, because we concat two tensors with 25 and 25 width, or height, or dimension. So, and we can provide a -1, which will mean take all the rest of the axis, the shape, and squash them together. So this will be the shape of it. But LC has the same shape now. So that's not good for image display. So let's format LC back. Still we need 50 frames. But we need 3 channels, 128 and 128. Now, these are basically the frames again. So we can compare how interpolation between the latents and then decoding those latents based on learned weights in the decoder versus just a plain linear interpolation between the images differ. As you can see, the interpolation with the autoencoder is much more structural. Okay. Now for what I promised. I found a study from 2016 for VAEs, and also it works for generative adversarial networks, GANs. And what it says is a simple equation. It's surprisingly simple and awesome. Is this. In latent space, if you take all the images that have a smile on them, average them, and subtract all the images without a smile, of course the average of them, that gives you a so-called smile vector in that latent space. So all these are latent vectors of those images. Now, I have this faces 128 dataset on my machine, and by now you probably have it too, but to handpick all these smiley images just from the training samples, which are 500, well, that would be a lot. So in this case, I use ChatGPT because I didn't want to deal with this, it's not my priority. And I have this notebook, it will be uploaded to the community as well, along with the main notebook. It installs OpenCV Python and uses an, well, you have to have your dataset folder if you want to run this. And it uses a simple HAR cascade OpenCV algorithm to detect smiles on faces, and then generates a smiles.txt file. Now I already generated that smiles.txt, renamed it to CSV. And basically these are the indices in the trained data set of those images that have a smile on them. So for example, image 4 and 5 have smiles. 14, 15 have smiles. 16, 18, and so on. It's not guaranteed to be completely accurate, and it's actually focused on grinning smiles rather than slight smiles. But you can use the CSV to continue with our examples, because we are going to make people smile. And for this, If you don't have, then install pandas, import it as PD, and I'm going to write a function here. You can use this decorator. Torch.nograd is the same as if you wrote with torch.nograd. Generate smile vector. And from the train data set, because that's what the smiles CSV is made for. So let's turn the model into evaluation. Read that smiles I have it. Where do I have it? I think I have it next to this notebook. Yes. And what we need to do basically is go through the whole train data set and collect the smiling pictures and the non-smiling pictures. Actually, we go through the whole data set, convert each image into its latent vector, and then collect these latent vectors into non-smiling or smiling tensors or arrays. So let's make two arrays, smiles, non-smiles, and iterate through our data set. And we need to encode each image. So IMG, which is a single tensor, unsqueeze it to add the batch dimension, move it to our GPU, and we will have a latent, no, actually we will have mu and logvar, and we can use VAE, reparameterize using that logvar and mu to get an actual sample latent vector. Now we have the index and our smiles df. So if the index is in smiles df, the index is the column name in the CSV, dot values, then we add it to the smiles array. As we add it to non-smiles array. And the equation says that we need the mean of the latents with smile and the mean of the latents with no smiles. So mean smile equals, we need to actually make a tensor of these smiles and non-smiles array to calculate the mean. So we have smiles, we concat them on dimension 0 to batch them, and calculate the mean on dimension 0. So we have a latent vector like this, below another latent vector, below another latent vector, and so on, grouped into two. And we have all these rows, and along dimension 0, which is in this case this, we average each value. So we will have, in the end, a single vector for mean smiles and mean non-smiles. Let's print the shape, just to be sure. And because this is a function, return mean smiles, mean non-smiles. Actually, we can just return the smile vector. So return, the smile vector is images with smile, so mean smiles, minus images without smiles. So we subtract it. Okay, let's call the function itself. So smile vector equals generate smile vector. Yes, because I wrongly appended the index, I'm sorry. So you append the Z. So the size of the mean smiles vector will be a vector of the latent, with the length of the latent dimension. Okay, now because we sample from this distribution, we have an encoded image, as I said. One image, when you encode it, it doesn't output a single latent vector. It outputs a mean and a variance, basically. And we just sample one random vector from it. But we could sample many because it's the same image, basically. So why not give a parameter and make samples, for example, 5. And we just run a loop with the same mu and log variance. So we generate multiple Zs and append it either to smiles or non-smiles. So in this way, actually, we can kind of come up with generated images in this latent space. So for each image, for example, if we have like 3,000 smiling images in our train data set of 5,000, if we sample 5 for each, we can use 15,000 images to make our smile vector stronger. So what can we do with this smile vector? Open another code block. Just make sure your model is in evaluation, but it already is. And pick an image that has no smile from the train data set. I will pull up, this is the train data set. Here, for example, 694 is the index. 694 with torch.nograd. Let's call our model on image no smile. On the batch dimension, move it to device. This will return the reconstructed image. It will return the latent vector and the mu and the log variance, which we don't need now. Now we can show the reconstructed image. Here. take Z, add the smile vector, use the model decoder on that Z, and we'll have another reconstructed image. That is smiling. We can even multiply the smile vector, and she's now really smiling. Also, face changes a little bit. So this is not a sophisticated technique, it's an old technique, 10 years old, but it's a really, really simple one. And it surprisingly works well, given our latent space is very structured and continuous. If you give horrifically high values, then it changes the image a lot. But yeah, you can experiment with it. Minus values, I'm not sure if it doesn't really, it gives horrific results. Oh, yeah, maybe she became a little more sad, but 1.5 still works. 1.75 kind of, but I guess the maximum is 1.5. All right, so why don't we go back to our cool example. Just copy this part. So we have take the same image. We have the smile vector, add it, deconstruct, but we will use this interpolation. You can remove the normal linear interpolation part. And we will have our alphas and betas. But instead of this, we have the original image reconstructed. Let's call it rec. We can leave it as rec, I think, and replace ZA with rec and ZB with rec smile. And actually we can, I think, we can keep the Z because we won't use it anywhere else. So this part of the code can stay the same as it was. We won't need these lines. This is just the alpha and beta calculation. We concat them, we come up with a phi that we can use for generating the frames. And not exactly, because we're not interpolating the images here, just wrote rec. So yeah, we use Z, this Z, not this Z. Too many variables of the same name. And then we don't add it here. We can use it as Z plus smile vector. And we will decode that Z. It's going to be 50 frames. And she's smiling back and forth. Now one more thing that you could do is import your own image. And I don't guarantee great results because as you can see, even here the reconstructed images are very blurry. Later we will work on diffusion models and make much better images, but for now this is simple and fun enough, I believe. Let's import pill and the image from it, and create a photo of yourself where you don't smile and make it kind of similar like these images, so only the face, but the face fully shown and a little background only. Now we have this TF variable from the topmost of our notebook, which is from torch vision transforms, and it has this toTensor function, which if you call it returns another function, and with that you can call image.open. I have it dataset/shandor.png. Can convert it to RGB, but I believe it's already in RGB. It will not hurt. With torch.nograd can go up. Addition, this is not, it's redundant here. I just left it there accidentally. So that's me, no smile. It's already a tensor, normalized in between 0 and 1. Unsqueeze it, device run the model. We have reconstructed image. Now we can even use the same code. I believe completely. Okay, if that doesn't work, then we can re-import from torch vision. I think it was transforms dot as whatever TF. Okay, Python doesn't like it. I have to go back and check how. We imported it actually as T, not TF. It's just torch vision.transforms. But it's already imported, so you can do T tensor. Yeah, that's according to the encoder and decoder, that's me. That's me smiling. Let's add a little bit more smile. I'm starting to wear glasses and look like a woman. Maybe that's too much. Yep, so this was the Variational Autoencoders episode. Thanks for sticking with me this long. So if you like the video, please click like. Please click subscribe and join our free Skool community, where all of this code, the notebooks, the videos, and many extras will be coming there exclusively. Thanks so much and see you next time.